Yep, we can see your screen.
Sweet. Thank you. So let's start. First, this is our team. I'm Nicholas, ZkApps Builders or two, and also the chief product officer at Cerebrum. Basically, at Cerebrum, we're building the future of self-sovereign identity and the layer of the new of identity of the new internet. Then we have Juan Pablo Garzon or JP Garzon, which is the co-founder at Macondo, where they allow you to invest in real estate from Latin America, starting from $50. Then we have Santi Rios. That it's a full stack developer at Cerebrum. And we have Cami that is not here, but she helped us a lot with the presentation. And she's always there for us. And she's the co-founder at Makers Fellowship, which is a LATAM fellowship and investor at B2 Founders. Also, as advisors, we of course have the great team from O1 Labs and Mina Foundation and a unicorn founder, which is Andres Bilbao. So basically, let's start with the why we build this solution. So one of our team members at some point wanted to invest in a crypto startup, and then they gave her their Ethereum address, and with their Ethereum address, we were able to see exactly how much amount of investment they had done previously, or they had received. So this is a big problem. And then when we talked to the business, they didn't know they could be tracked and were not aware of the lack of privacy. So basically, I think that this makes the point of why asymmetry of information is important. Probably each one of you have a different example why you guys care about privacy, but for us, it started like this. So then we see right now that the blockchain is similar to a Twitter of your bank account, and of course, a lack of privacy is still hinders the adoption of businesses. So it's just basically imagine that every time that you're buying something, everyone is aware of it. It kind of sucks. So that's what we thought. And then we built Minado, which is a mixture based on the proposal used by Tornado Cash. We started to develop and work on it on the Ethereum Bogota hackathon. Before we worked on a state addresses approach, and then we realized that it's possible, but it's not feasible in Mina. So we started developing this mixer solution. So basically, this mixer solution allows you to do private transactions. Then we focus a lot that it's a simple user experience, and it was designed for Mina Protocol. So here I have a demo, but I think that we can run a live demo as well. So if you go to the live side, the first thing that you gotta do is deploy. The reason why it's because we're still working on the integration with Berkeley Testnet. Then you would connect your wallet. That for now is a Mo wallet. That it's another step that we have to make. That it's connecting this to our wallet. After you're connected, basically what we would do is transfer the funds. So this would be your node. With this node, is the way that you're going to go back and withdraw your funds, and it's how you can do it in a private manner. So as you can see here, we transferred to the ZkApp 1 Mina, and then the user that had an initial balance of 1,000 Mina now has 999 Mina. So when we go to withdraw and we copy the node, and then we click withdraw, basically it would release the funds. And we're gonna take a look at how this works underneath the hood, but I just wanted to show you our user interface. And as you saw, it's really simple, and we focus a lot on having as few steps as we could. So sorry, I already saw that. Okay, cool. So how does this work underneath the hood? So as we saw, the first thing that the user does is depositing. So the user selects a predefined amount of funds to deposit. So in our case, we have 1 Mina, 10 Mina, and 100 Mina. The reason why it's because we need to keep privacy, of course. So for example, if someone deposits 1.11 Mina, then if that same person withdraws it, or someone else withdraws 1.11, it's really easy to track that it was that person. So that's why we have 1, 10, and 100, which is arbitrary amounts. Then the first thing that happens is that we create a secret. which we're gonna see in the following slide more in detail what it is. Then we generate a nullifier. The nullifier would avoid using a node twice, so it would avoid double spending when we're drawing. Then from this nullifier and the secret, a commitment will be created. This commitment will be inserted into a MERKLE tree. So after the commitment is created and the node is created, we will insert this commitment into a MERKLE tree. So then in the withdraw side, the user, as you saw, the user provides the node. Then after the user provides the node, our smart contract verifies the node is part of the MERKLE tree using a MERKLE path verification. And then it validates that the nullifier was not spent before, so to avoid double spending. So, and then it withdraws the funds. So I'm gonna go a little bit more in detail about how the deposit works. So the way the deposit works is, as I said, our smart contract will receive the funds. Then we would generate a secret. We would generate a nullifier, which basically is the hash between the public key of the user and then a random private key. For this, we use Poseidon. And then after this, we would hash the secret and the nullifier. And we will check that the amount of Mina is correct. After all of these conditions and all of this process is done, we would just update the MERKLE tree. So here, I would pass it to JP.
Yeah, of course. Basically, that is what is happening under the hood for the deposit. So basically, we deposit a commitment as a leaf to the last leaf that was not added. So like to the last leaf that is available. So we put that commitment into the leaf, and then the MERKLE tree rebuilds up, and we store the MERKLE root, which is a new MERKLE root every time someone's deposit, because actually the MERKLE tree is changing. And now we have two approaches, two implementations for storing the MERKLE tree. Basically, from one side, we have a deposit event implementation, where every time when a user makes a commitment, we raise an event, a deposit event that stores which commitment was released, and then we rebuild up from all the commitments. And we have another approach, which is basically implementing off-chain storage directly to not necessarily have to rebuild all the MERKLE tree. This is an example of the deposit class, that we use for the event. Basically, in the approach of the event, we are storing three main things: a commitment, the leaf index, which is specifically the leaf index where the commitment is on the MERKLE tree to make easier to access to that commitment, and then we have the timestamp where, like, to know where the commitment was put into the MERKLE tree. Now, when we are on the withdrawal, as Nico explained, basically the user only has to provide the node, and then basically that node, how it looks, it's on a string with certain format, and then we take that node, we use regular expressions to obtain the information, and from that information we have things as the amount that was deposited, the currency. Like in this moment we only accept Mina, but maybe in the future we could integrate different types of currencies. And then we extract from that node the secret and the nullifier. From the secret and the nullifier, we build up the commitment, and also we reconstruct the MERKLE tree from the events or the off-chain state, and then we generate a MERKLE tree witness, which, like, I'm going to explain more graphically in the next slide, please, Nico. Basically, how it looks like, which is easier to see graphically, how it looks like. The witness is basically the path do you need to rebuild the MERKLE tree from the commitment do you have. So basically, you do not need to build the proof, the MERKLE witness. Do you don't need all the leaves, all the MERKLE tree? You only need the commitment and all the adjacent hashes that you need to rebuild up the MERKLE root until the end. Once do you have the MERKLE root build up from the commitment that the user provides with the node, you can compare that to the MERKLE root that is stored in the smart contract. And basically you make that comparison, and do you transform that into a zero knowledge proof that proves to the smart contract that actually that comparison is true. And also, do you need to provide another zero knowledge proof with the nullifier? Because actually the nullifier is the piece of information that allows us to track which user have already made that withdrawal and avoid double spending. So basically each time a user pass a nullifier, we store that nullifier in the smart contract as an event as well. And in moment of withdrawal, we only have to review the nullifier and know and see if the nullifier has not been expended yet. And that's it. The funds are released after that proof. Lastly, like as we explain you, we take as example Tornado Cash, we take as proxy Tornado. So basically we need to understand how Tornado code works and how they make all the processes. And in this process of understanding Tornado, we realize that doing the same thing, doing Minado, actually doing a mixer in Mina has a couple of important advantages. The first one is the efficiency of the hash functions. So basically, Tornado Cash uses Fedorsen hash, and Mina uses another hash that it's called Poseidon that was released in a research paper a couple of years ago. And basically, the advantage is that Poseidon hash is 8 times fewer, have 8 times fewer constraints per message bit than Fedorsen hash, and actually that ends up being really faster in comparison. Then we realized that the maintenance is easier and more scalable, because actually, if you want to implement this on Tornado, do you need to integrate zkApps, which is a third-party library to build up the circuits between JS, between the smart contract, between Solidity. So actually, to contribute here in Mina with Minado, do you not need to understand specifically the templates that do you need to build for develop the circuits and all of that? You only need to understand how the basic code works, because actually Mina transform all the interactions under the hood to a zero knowledge proof. And then of course is really important the scalability in terms of how cheap is to make a transaction, and basically despite the transition of from proof of work to proof of stake in the merge from Ethereum, Mina is still being cheaper than Ethereum, so we can enable use cases with lower amounts, basically. Yeah.
So before I go into what we achieved so far, I would want to ask if there are any questions about the deposit or withdrawal logic or the implementation using events. Let me see the chat.
Just a quick question to the previous slide. How did you guys figure out it was 8 times faster?
Oh,
Yep.
This is actually in this research paper, if I'm not mistaken, JP, right?
Yeah, I'm going to send the paper where Poseidon hash comes from. We read the paper because actually it was real interesting. We read out and they explain how they build up these 8 times faster. They have tables of comparison between Fedorsen and Poseidon, and it's really fun if you want to read it.
Got it. Thanks.
Cool.
Brent, there's a question from Brent, but I don't know if that's something you want
we can do it separately. I'm curious about how the MERKLE root updates work, but that might be out of scope for. Let's just get back to the presentation.
Okay.
No, I think this is a good thing at the end, though. I think this is an interesting question. Yeah. So it's up to you guys. If you have more stuff to present, like keep on with your presentation, or answer Brent's question now. It's up to you, but yeah.
Okay, if you want, let's finish this. We're just missing 2 slides, and then we can answer your question.
Great.
So what we achieved, so the first thing that we achieved is doing the deposit logic, then the withdrawal logic. Also, we achieved the implementation using events, also implementation using single server off-chain storage. We're still developing the implementation using MERKLE's testnet. And then we are also still writing some comprehensive tests. Then the last thing that we didn't achieve is the implementation using a multi-server storage. The reason why is that there is not still off-chain multi-server storage in Mina, and this takes us to the next steps. So in the future, the vision of our project is not just a mixer, is more privacy network rollup that enables more builders to create a ZkApps on top of Mina Protocol. For example, DeFi private protocols or lending private applications or staking or private staking applications. It would be something similar, or we envision it something similar as Aztec, but built from the ground for Mina. So before working on doing on something like this, we realized that we need two things. The first one is improving off-chain storage. As I said, there is not still a possibility of scale our solution because there is no multi-state storage, and we think that it's crucial for scalability. So after implementing single-state off-chain storage, we saw that there are a lot of things still to improve in terms of off-chain storage. So that's why we are applying for a grant, and we want to keep working on off-chain storage. The other possibility is, as we spend 80% of our time building Minado was spent in MERKLE trees or handling MERKLE trees and working with MERKLE trees, we realized that there are a lot of limitations still to the MERKLE trees libraries. For example, there is no MERKLE tree sorting, which was something that we needed, and there are no math functions for MERKLE trees. So this is something that we're interested in working, and we'll keep working on the future on this. So here I'm gonna pass it to Santi, where we can take a look at the code real quick and then finish our presentation. So I'm gonna go to the GitHub of our UI. And then I'll pass it to you, Santi.
Oh, yeah, thank you, Nico. So to keep it simple, the structure of the repo is like a mono-repo to use for make changes quickly, and this is for mainly testing purposes. Yeah. So the structure is the front end is building in React, and the connection with the smart contract is through a compilation and using a local instance of the Mina blockchain, as Nico explained at the beginning. So this allows us to access to the functions exposed in their smart contract and interact with the mixer in this case. So the state manager of the React application is, we are using just the React the native state management React functions. So yeah, and we start the application through an HTTP serve locally. So the improvements that we can do to this project is separate the logic and improve the structure of the front end, in order to dedicate more time building the logic of the smart contracts, because right now is a little complicated, but we are going to improve that in order to dedicate more time in the important thing that is in the smart contract logic. So that's a quick overview about the structure of the repo. So yeah.
Yeah, thank you, Santi. So actually, the way that we worked on this was, first we developed the CLI that was all the logic, but just using the CLI, and then we tie that with the front end. So in the smart contract, if you want to test this out, you can go to the init test function. In the init test function, you are going to see the two basic functions. You're going to see deposit and then withdraw. So when you go to deposit, you can see more in detail how the deposit works, and you can check that what we said in the presentation is true. And also, of course, we're open to feedback, and you can also add GitHub issues if you see something that it's not working properly in our GitHub. Then you can also click on withdraw. That, as we told you, it receives a node string from the user, and you can check how the logic works on the withdraw side also. And again, if you see anything that it's not working properly or anything that you would change, or potential vulnerabilities, we are happy to get your feedback. So I think that's it. Thank you so much. And again, thank you, Jack. Thank you, Regina. Thank you, Florian, and everyone from the Mina team and O1 Labs team for all your help. It was amazing.